Welcome to Microlecture 24 on conformational analysis of disubstituted cyclohexanes. Okay, so here we have two different named molecules. The first one is trans 1-ethyl 2-methyl cyclohexane, and we want to draw the chair conformations of each. So I would always start out with the flat structure. We're comfortable using dash and wedge on flat structures. Remember, dash and wedge would never ever go on a chair structure. So I'm going to start with the 1-ethyl, and I'm just going to orient it one way or the other, dash or wedge, doesn't matter. And then if that's carbon 1, then the next one over must be carbon 2, so it has a methyl. And I want to situate that on the opposite face of the ring because trans means opposite face. So this is a trans 1-ethyl 2-methyl cyclohexane. So the trick, the shortcut for converting between the flat structure and the chair structure is to put your D's together. So dash is always going to equal downward on your chair structure, and so the opposite is then true as well. The wedge is going to be pointed upward. So let's go ahead and draw a chair structure, and then I'm going to make the upward pointing nose my focal point. I see that the ethyl group is down, and the down position on that particular carbon is always going to be equatorial this way. So that's where I'm going to start, and I'm going to draw my ethyl group there. And then one carbon over, doesn't matter whether you go clockwise or counterclockwise, is going to be the up position for the methyl. And so I'm just going to draw my methyl group pointed upward right there. So one's downward, one's upward, and I know that the methyl that I just drew has to be equatorial because the only upward position on that carbon is equatorial. Let's say that I went around clockwise instead. It's going to be the same situation because over here the upward position is equatorial. The downward position for those carbon atoms is axial, and so just to be clear, I'll draw in the down axial hydrogen atoms and the up axial hydrogen atom that is on the first carbon. So draw those hydrogen atoms in if it helps you. Let's move on to the next problem. So the next one is cis 1-ethyl 2-methyl. So it's the same compound, and the only difference is that they're both of the substituents are going to be on the dash or both on the wedge, doesn't matter. So I'm going to draw them both on a wedge, and that means that they are both pointed upward. All right, and so I'm going to draw the chair structure for this compound. Find my upward pointing nose, that's always my carbon 1. And I have an ethyl group on there, so up is axial on that carbon. And the next carbon over, clockwise or counterclockwise, we already did it on the previous example, is upward equatorial for that methyl. So that's how you convert to a chair structure from a flat structure. Just remember, dash equals down, wedge equals up. And you have to know whether these up and down positions on each carbon are axial or equatorial. So it takes a little bit of practice. I would say, just get your hands on as many practice problems as possible for converting flat structures to chair structures. The first structure here has an isopropyl group pointed down, and so I would point the isopropyl group down. We can ring flip, and so let's practice doing a ring flip for this particular compound. So right now I've drawn the isopropyl group equatorial down, and let me draw my ring flipped structure. And the isopropyl group is now going to be down still, but it's going to be axial down. Okay. So the next example is a cis relationship between a methyl and a tert-butyl. So first let me draw one chair structure, knowing that a wedge is up, and I like to start at this carbon right here. So I'm going to draw my methyl group up, which is axial on that carbon. The next carbon over the up position is equatorial. So I'm going to draw a tert-butyl in the equatorial up position, and I'm going to ring flip this. So I'll draw my ring flipped chair, and the tert-butyl, which was pointed upward there, is still going to be upward, but it's upward axial now. And the methyl group, which was upward, is upward equatorial now. Okay, so the next type of problem is going to involve looking up energies on a table. I have my source of data right here. This is an excellent table providing 1,3-diaxial strain energies for all of these substituents with 2 hydrogen atoms. So, for example, in the first structure that's drawn, if this is carbon number 1, then carbon number 3 going in a clockwise direction is right here, and there's an axial hydrogen on there. And of course this tert-butyl is interacting via 1,3-diaxial strain with that carbon atom. If I numbered around counterclockwise, then this carbon would be number 3, and it also has an axial hydrogen atom. And so it's these 1,3-diaxial interactions that we've been talking about, and these are the energies that are tabulated in this table on this slide. So having a tert-butyl in an axial position is energetically more costly, as you can imagine, than having a methyl in an axial position. So let's find the tert-butyl group on this table, and we see that in kilocalories, it's 4.8 kilocalories per mole to have that tert-butyl in a axial position. So that's about 5 kilocalories. The structure right next to it, to the right of it, the tert-butyl is now equatorial, so it's the ring-flipped structure, and the methyl is the one that's going to be costing us some energy. So that's a CH3 group right there. It's interacting with this hydrogen atom and this hydrogen atom via 1,3-diaxial strain, and it is costing, if we look at the table, it's costing 1.7 kcals per mole to have that methyl group in the axial position. So if we looked at the energy difference, we could get an idea about which disubstituted cyclohexane is more stable. And so being that the difference is about 3.3 kcals, we know that it's considerably more stable to have a methyl in the axial position than a tert-butyl. So one thing is to be